using backscattering tool. It will look at a little bit higher K, but is also sensitive to flow. And so he'll use that in a variety of physics studies on D3D. Go ahead.
Thanks very much for the invitation to speak. Can you hear me well? I would like to thank my co-workers at various universities and also the D3D team for the support in the experiments. So this talk, as in contrast to the preceding talks, will deal with intermediate and smaller scale turbulence, which we find is important in, especially in low collisionality H-mode regimes. Understanding electron thermal transport in H-mode plasmas is critical for next step burning plasma experiments such as ITER. Electron transport is intrinsically driven by multi-scale phenomena. So local measurements of intermediate and smaller scale density fluctuations up to the electron gyro scale here have become available only fairly recently. And I will particularly focus on experimental results from the Doppler backscattering diagnostics, which has the ability to probe a large range in radius as well as wave number. Gyrokinetic code results have been obtained for a while that have predicted that intermediate and small scale turbulence may be important or possibly dominant in H mode. These are Gini results from Frankienko and co-workers, and also gyro results that have been obtained in the US. Local multi-scale turbulence measurements provide critical tests and validation of gyrokinetic predictive codes. This is a brief outline of the talk. After a short introduction, I will focus on core turbulence behavior across the LH transition. Again, as I mentioned, in low collisionality, high temperature H modes. Multi-scale turbulence measurements in these plasmas have been obtained. We will look at radial profiles, wave number spectrum, linear stability calculations using the trapped lambda fluid code, the TGLF code, and then finally gyro simulations. And then I will briefly review some very recent experiments where we have successfully increased the electron to ion temperature in these very low collisionality QH mode plasmas to 1. Then if there's time, I will review some zonal flow measurements that have been done with Doppler backscattering recently also. This is the result from the Gini calculations that Frankienko and co-workers obtained from a PL in 2008. This is basically a cyclone-based case. Our LTE is 6.9. The ion temperature gradient is about 10% above the critical gradient, so ITG mode is marginally unstable. The density gradient is 0 here. And we can see that there's a high K feature here between 1 and 10 that is visible and contributes about 50% of the electron heat flux here. Now, if the ion temperature gradient mode is excluded, so in this case the ion temperature gradient as well as the density gradient is 0, so there's no ITG mode, then this percentage goes up to about 70%. So 70% of the transport is driven by KOS of larger than 0.5. And here I've just indicated that we have BES measurements that can access the low K regime that George has talked about in detail, of about up to about KOS of 1, slightly below 1. And then we have overlapping measurements in the from the Doppler backscattering diagnostic that can go all the way up into the transport relevant ETG range here up to about KOS of 7 in some cases.
Sorry, clarification question.
Yes.
The only difference between the top and bottom curve is that you increase the ion temperature gradient in the top curve.
Well, this is no ITG mode at all. This is ITG close to marginal stability, but still unstable, as if I understand.
Transport level dropped.
The total transport level went up here. Actually, there's a completely different dynamics now in this case. So this is larger transport than here. Maybe Frank can actually.
I just hadn't remembered the sign of this result. I thought it was.
No, what you're thinking of is probably strong ITG and weak ITG. And
there's another case
that's
that's not
third
shown
curve
here.
which is not shown here.
Right.
Right. So that difference I understand, but here you raise the ion temperature and the transport drops.
Well, that's the electron channel. Remember, there's also an ion channel, and you
This is only
transition.
Chi-e.
The
Fine,
lower
okay.
part is TM,
Yes.
and the upper is ITG
Okay.
dominated.
Okay. Now I understand. Okay.
Yes, it's also the TM and ETG here in this case. Okay. Just because most people are not familiar with Doppler backscattering yet, here's a brief explanation of the principle. So the idea is to launch a Gaussian well-collimated microwave beam at an angle to the flux surface. So this is different from conventional reflectometry. And as a result of refraction, this beam is deflected in the plasma here. The refractive index, which we obtained from ray tracing calculations, goes down. So this is just the ratio of the local wave number over the vacuum microwave wave number, and that goes down as we approach the microwave cutoff here. Now, as a result of three-wave interactions between the incident microwave beam and the turbulence, there's a scattering going on. And since we use the same optics to launch and receive the microwave beam, we're looking essentially at backscattering. And there's three-wave selection rules that apply here. So the scattered wave number is incident minus the fluctuation wave number. That means the fluctuation number is minus 2 times the local microwave wave number at the cutoff or at this inflection point here. Since the turbulence spectrum depends strongly on k and usually decreases at some power of k, this essentially tends to localize backscattering to the cutoff layer. But we use, in some cases, a distinction between Doppler shifted feature and non-Doppler shifted features. If you integrate over the radial part of the response here, you will get a non-Doppler shifted feature, and then you get a local reflection or a local backscattering feature from the cutoff that is heavily Doppler shifted, and this allows us to distinguish between local and non-localized scattering. The backscattered amplitude is proportional to the density fluctuation. This is has been shown in full wave calculation. This is something that cannot be established with ray tracing. You need really two-dimensional full wave calculations that have been, for example, carried out in Stuttgart by Carsten Lechte and other workers also in the US. The Doppler shift is essentially obtained from the frequency displacement here divided by the resonant wave number here that I have defined here. There's an intrinsic part in the velocity response that comes from the intrinsic dispersion of the turbulence. In many cases here we look at heavily rotating plasma so that this intrinsic dispersion is completely, the phase velocity of the turbulence is negligible compared to the equals p velocity. This shows the localization of the two systems on D3D. There's a 60-degree system that has 8 channels, and here's, for an example, plasma, the ray tracing outlines here of the ray trajectories of these channels. There's another 5-channel system located 180 degrees opposite at a different toroidal location, and you can move these 5 channels to some extent in this range here, so you can overlap them or use them to fill the gap between the outer 4 and the inner 4 channels here. And this is actually a typical density profile of the plasmas that I will be describing in the remainder of the talk. So these are low density plasmas with about 1 to 2 times 10 to 13 pedestal density, going up to about 3 to 4 in the core. And this just is an example localization of the different Doppler channels here. So we get very good information both in the upper pedestal and to some extent in the inner core plasma up to about hour value of 0.4. The wave numbers we can measure are between 0.5 and 15 inverse centimeter. The radial resolution is better than 0.5 centimeter. The wave number resolution depends on the local curvature of the flux surfaces as well as the size of the microwave beam. The Gaussian microwave beam is described here by the width W0. And this leads to a k response function between 0.2 and 0.5. So delta k over k is about 0.2 to 0.5 with the higher resolution obtained here on the outer flux surfaces and then the inner, the lower resolution obtained in the core. So now I go right into the data. This is an LH transition in a low collisionarity H mode plasma, low collisionarity plasma, low density plasma that occurs here at about 1100 milliseconds into the shot. What is shown here is electron temperature traces from ECE, from the ECE diagnostic. And we see that there's a very fast increase of the electron temperature both near the pedestal here at 0.9, but all the way up to the core with some time delay here. Going from values here of 1 kilovolt to about 2 kilovolt pedestal temperature, and then in the core we're going up to about 6 kilovolts here. When you look at this time slice around the LH transition in an expanded plot here, we have now combined this with transport results, a time-dependent transport analysis from TRANS, And we basically see that the electron temperature starts to change first here in the pedestal as expected, and then with some small delay that is only on the order of a couple of milliseconds. This is again the LH transition time indicated by the H alpha drop here. And we can see that there's changes in the electron diffusivity all the way from the edge to the core. So very dramatic changes, fast changes here in the pedestal, but also on almost the same time scale here in the core. And it keeps going down here to a very low value of about 0.3 meters squared per second. So now we look at the fluctuation dynamics across the LH transition. This is first here the BES signal that drops very fast. We're looking now at our value of 0.7 here, so inside the core plasma, not in the deep core. Sensitive to wave numbers of about up to about 0.5 here. And then we also look at temperature fluctuations. This is the same data that Anne presented before in her talk. So we see the temperature fluctuations here going down to a level that is not measurable anymore within the signal-to-noise response of the diagnostic. When we look at higher K, this is now Doppler backscattering results. This is looking at our A of 0.4. We see that the low K fluctuations show similar behavior here to the BS. There's some drop before the LH transition because the rotation is already picking up. But then there's a reduction by about a factor 3 or 4 here at the transition, and further slow decay here after the transition. But the important new information is now that this also in these plasmas occurs for higher wave numbers. So this is KOS of 2. And we see again a downdrift, and we see a precipitous change here at the LH transition deep in the core. So this is something that happens only in low collisionality, low density plasmas, where there's a sufficient amount of shear in the core plasma, and then I show the corresponding profiles in a moment. This shows now the time evolution of the E cross B shear across the LH transition. This is the beam power step to about 7 megawatts that induces the transition. Here's the H alpha trace again. And this is from linear stability calculations now the maximum growth rate in the normalized by A over CS in the ITG TM range, and then in blue in the ETG range. And notice that there's a different scale here. So the ETG growth rates are of course always much higher than the TM ITG growth rate. So as the shear picks up here, even before the LH transition, the low K growth rate becomes marginal. So the A cross B shearing rate becomes very close to the linear growth rate here at the time of the LH transition, while the ETG growth rate, of course, stays much above. And what is compared here is actually the normalized growth rate compared to the E cross B quench rate. So that's the Waltz shearing rate. So it's the Hamburel shearing rate translated into a flux function, and then it has an additional factor here that is proportional to the square root of the elongation that was established by using a systematic variation of the shearing rate in gyro to actually find the quench point. So this is actually enables us to directly compare growth rates and E cross B shearing rates. Here on the left side, that's for our value of 0.4. Most of the results that are shown now are localized. This just shows the linear growth rate calculations for the Elwood case here in blue with the very clear ITG feature here. The shearing rate in this case is very low. And then after the LH transition here, about 1150 milliseconds, we have a shift to the TEM range here. So there's no clear ITG feature anymore as a result of the changes in gradients. And at the same time, the shearing rate is now large enough to suppress activity up to about a wave number of 4. So this is essentially eliminating the TM and ITG range. We can conclude that the resulting transport results from high K, the resulting electron transport results from high K modes.
Sorry, but are you going to show us whether it's actually doing that?
I hope so. So these are the equilibrium profiles in L and H mode. So you can see that these plasmas have very high pedestal temperatures between 3 and 4 keV for the ions. And then they have actually somewhat of a distributed transport barrier. It's not a very localized ion transport barrier, but they have a transport barrier-like behavior in the core. The electron temperature here in the pedestal is about 2 kilovolts, going up to about 5 kilovolts in the core. And this is now the shearing rate that I showed before, but this is the whole entire radial profile. So in blue, the L mode case, where there's essentially no shear, just a shear here in the edge. And then the electric field becomes very negative here at the LH transition. There's a low point here at in this particular time slice where the shear is not much changed, but there's this very broad increased region of shear here in the core that is very likely responsible for the ion internal transport barrier here, and also for the suppression of the ITG-TM feature that we have seen. I should mention that these are very low collisionarity plasmas that are indeed comparable to the eta collisionarity. Of course, our density is much lower than the target densities for eta here. Nevertheless, this makes it a very interesting test bed to look at electron transport in the context of burning plasma relevant physics. So these are now full fluctuation profiles from DBS for the L and H mode discharges that I showed. So we see here the suppression in the pedestal in H mode. And we see that inside of about R/A of 0.6, there's substantial reduction in fluctuation level. It's more than an order of magnitude, and I show not the square fluctuation level, but the linear normalized fluctuation level here. So these are very substantial changes here. This is done here for KOS of 0.5. And some of this effect persists at the higher wave numbers here, so not much change here in the edge, but you can see that in the core, especially here inside of 0.5, there's a very dramatic decrease in the intermediate scale fluctuation levels and very low fluctuation levels in the high K. In the high K case, we cannot access the data for with Doppler backscattering in the L mode phase because the electron temperature is not high enough, so we're looking at a different KOS there. This is now a comparison of the linear growth rate calculations and the fluctuation levels. So we have taken all our different measurements that were obtained in different shots with different angles of the Doppler backscattering system and constructed basically a fluctuation level spectrum versus KOS. And you can see here in blue the L mode phase and in red the H mode phase. There's a clear flattening now here at R/A of 0.4. The spectrum is essentially flat here in this region, and then there's a dramatic increase here. I should mention that the L mode spectra are best fitted by an exponential, not by a power law. And this is the relationship here with a factor of 1.5 to 1.7 here for the exponential. The suppression region here that we determined from the linear stability calculation is indicated here. So at R/A 0.4 we suppress out to about KOS of 4. At the outer radius here, we suppress up to about KOS of 1, by comparing the French rates here with the linear growth rates. And these regions here correspond to the regions where we see reduced fluctuations. So here we see reduced fluctuations up to KOS of 3.5. In this case, we see reduced fluctuations up to about 1. And there's possibly a secondary peak here. So a flattening of the spectrum, possibly a secondary peak here also.
Just for clarification, OS is built with the electron temperature or the ion temperature?
In this case, the ion temperature is still larger than the electron temperature. I showed the.
So I mean the definition of OS.
Oh no, the electron temperature only was used. In the definition, only the electron temperature was used.
So square root of T. Now, if I would like to know KY, what would be the correcting factor? I would have to.
That would be if we. I mean, you can see here from the relation that at 0.4 the correction factor would be about square root of 2, I would say. Almost square root of 2. And then further out here, the temperatures are more similar. So there's not much correction at 0.6, but at 0.4 there's a correction about square root of 2.
So could you just ask about the previous?
Before the one that I showed here, this
The
one.
one about the suppression. Yes.
This one? Okay.
So this level of suppression of turbulence, does this mean that transport is now predominantly collisional? Is this still turbulence transport?
The ion transport itself, these are plasmas that have a very large hot ion fraction. So we are now in the process of really accounting for this. So in terms of the ion transport, things are not straightforward. So there's a distinction to be made between bulk ion transport and hot ion transport. And we do this by making comparisons to the neutron rate and the diamagnetism, basically. The electron transport is, of course, still turbulent, but it's much above neoclassical electron transport. But the ion transport is reasonably close to neoclassical, maybe a factor 2, but not
Above it.
above.
I was wondering, when you say exponential spectra, to which region in phase space does this apply?
This is only applying to L mode now. So this in this
Which part of K space?
Up to KOS, right?
about 3 KOS of 3.
So between 0 and 3.
Yeah, both cases here. Yeah. So these are now preliminary gyro calculations. These are not yet flux match calculations. So we don't start with an equilibrium profile and adjust the fluxes to be equal from these simulations. So this is just done with a fixed gradient simulation. Consequently, the gyro electron heat flux does not match the experimental. It only accounts for about 27 or 28% of it. This is the KOS spectrum of the potential fluctuations. In this case, there was a post-processing problem with the density fluctuation output. This is a very recent one, so I decided to substitute this out after visually convincing myself that there's not much difference between the spectral response in density and temperature, in density and potential here. And this is the virtual diagnostics for DBS. DBS only looks at Kr of 0, and this is the sum of the spectrum averaged over integrated over the Kr spread in the spectrum. So what we see is basically a clear peak here in the ETG region, and this is reflected here also in the electron transport. This is the electron transport, electron heat flux spectrum that peaks about at KOS of 5 here, and then a very steep decline in the higher K region here. Notice that the electron scale is indicated here also, so this corresponds to about KOE of 0.2 here, this peak. And then what happens with Doppler backscattering is also that the spectral index that we measure is smaller than the index that you obtained by integrating over the Kr spectrum, and I will show in a moment where this comes from. This is the 2D outboard midplane density fluctuation reconstruction from gyro. We see this ETG peak here at KOS of between KOS of 5 and 10 very predominantly. And we see also a low K peak here that is situated close to the first 2 bins of the simulation. The simulation starts at KOS of 0.25. It's a multi-scale simulation that we hopefully eventually can extend down to KOS of 0.1. And when you now take, this is difficult to see here, but when you can now see when you take a slice along the Kr of 0 point here, you get a faster decay here than when you take a slice, for example, here on the side. So when you integrate over the whole Kr spectrum, you will always get a much lower spectral index than when you integrate along Kr of 0. And this is borne out here in the data. There's not really quite enough statistics here, but you can see that both in L mode and in H mode, on the high K side, the spectral indices are quite large, between 6 and 8, whereas the simulation typically would indicate that the integrated spectrum has more decay index of between 3 and 4. These are just snapshots of the density fluctuation here at the outboard midplane. This is an L mode case, a different shot but similar parameters, and this is the H mode case. There's a factor 2 difference here in the number of gyro radii that we look like, but it's clearly dominated here by high K activity with some elongated structures in the radial direction here, and then this is of course a typical ITG case that Anne showed in great detail before.
At what radius is this? At what radius?
This is done at 0.6. The gyro, I forgot to mention that. All the gyro results are obtained at 0.6, RV of 0.6. This is now a recent experimental result that we obtained by decreasing the density somewhat with a slightly higher density gradient. This is a different shot, also QH mode regime, low collisionality, very similar temperatures and densities. And here we actually saw for the first time a clear feature that was going beyond the flattening that we had seen before. So we see the decay here in the low K range, and then we see a very clear feature here in the electron relevant transport regime. But the different colors are two different time slices that are very close together though. So that was just to improve the statistics. We looked at two different time slices here. And I have overlaid, we haven't done a gyro simulation for this case yet, but I have overlaid this on the previous simulation just to show that we see a feature in a similar K range here. But in general, our impression so far is that the experimental spectra show still more low K activity than the gyro simulation. So this has been the case for several simulations that we have done now. The gyros tends to place most of the transport here in this ETG dominated regime, whereas we see low K activity in the experiment. Of course, this has to do possibly with the fact that we're not matching yet the fluxes, so there's subtle differences in the ion temperature gradient and also the cross-bead shear that could possibly account for this. So this will be sorted out as we go on to flux limited calculations. So now the next topic I want to briefly touch on are very recent experiments that we have done where we have added central ECH to the plasmas that I have described before. So we start with a very similar setup with a low density, fairly high beam power plasma that goes into H mode here at about, in this case, 1100 milliseconds. And then we add ECH here at about 1700 milliseconds. So on the ECH power is about half of the beam power. So it's about almost 3 megawatts of ECH power. So this allows us to increase the central electron temperature quite substantially and the electron temperature gradient. So we see that there's a change here in the central channels from 6 to about 11 keV. And interestingly enough, there's a deterioration now in global confinement by about 20% here. There's a loss of momentum, the toroidal rotation is reduced, and the ion temperature is reduced here. So there's clearly a loss in ion confinement when we do this. These are the profiles that we obtained here. This is the beam injected case here, and when we add ECH, we double the electron temperature essentially in the core. So we have now a situation where TE is larger than TI, and we see that there's flattening of the ion temperature gradient. So we have basically increase of the ion transport, but we have high pedestal temperatures, so we have suppression of turbulence in the pedestal that remains, but we have loss of ion confinement in the core. When you look at the shearing rate now, the shearing rate has been reduced by about 60% here from the case that the case without ECH. So there's a substantial drop here in shearing in the central region of the plasma. And this table just shows the TE over TI ratios that we obtain. We go from about 0.6 to 1.2 in the inner core, and then the difference here in the outer part of the plasma is not as dramatic. This is just a 2D representation of the growth rates from a linear stability calculation to see what the tendencies are in these plasmas here. This was done in the low K range here, so KOS of 0.3. And we have here ITG dominated start condition. The positive frequencies here correspond to ITG, negative frequencies correspond to TEM. And when we push the electron temperature gradient up, simultaneously reducing the ion temperature gradient due to transport, we're going into the TM range here. And so the growth rate doesn't change very much. The TE over TI ratio, of course, changes in the core by about a factor of 2. So this is for R over A of 0.4 in the inner core. So we have a situation where there's transition from ITG turbulence to TEM turbulence here. And the variable that has been left out in the last calculation was the electron temperature gradient. So we have to account for the changing electron temperature gradient also. So the final state actually shows that the TM turbulence is increased here compared to the growth rates that we had before. And you can see the TM boundary has now shifted inwards here a little bit. So we're going in a very, very clearly TM dominated regime now. We can do the same comparison now for high K here. This is the ETG regime. This is the critical gradient here. In the base case condition here, before the ECH, we're sitting close to the critical gradient, and then we're moving into the ETG mode stays unstable. We're moving actually here as the electron temperature gradient increases, we're moving deeper into the ETG regime. So this is what I had so far on the QH mode plasmas. I'm not sure how much time we have, whether we have to
Do it in a couple of minutes, a few minutes.
Okay, so I just wanted to briefly touch on some measurements of zonal flows that we have used the Doppler backscattering system. Zonal flows, of course, normally are thought to influence mainly ETG scale turbulence, so the intermediate influence on intermediate and small scale turbulence is less well understood. We present evidence of a CF-induced shear layer and intermediate scale fluctuation suppression near the Q. This is supposed to be Q equals 2 rational surfaces. And this fluctuation suppression sustains an L-mode electron transport area at the Q equals 2 surface here. So this is now an L-mode plasma here, and you can see in this transport barrier that is established at about 1,000 milliseconds, lasts about 200 milliseconds. There's a very steep increase in the inverse electron temperature gradient scale length here. We have our 4 DBS channels from one of the systems that are described, and this red curve here describes the trajectory of these channels as the discharge evolves. And this is the location of the Q equals 2 surface from MSE measurements. So when we look at the flow velocity, we see that there's a local shear layer formed here near the Q equals 2 surface. So there's a couple kilometers per second difference in toroidal flow, which sets up a very strong local shear here. We'll go over the next one. When you now take adjacent velocity measurements, divide by the distance between the channels, you can establish the local shearing rate here. And this is near the bottom of the electric field well here. There's not much shear, but on the outer channels there's opposite shear, negative shear, positive shear. And this in time at some point the barrier actually collapses altogether. What we see now is that as the shear increases here, the fluctuation level in the intermediate K range, this is KYS of about 3 or 6 centimeters inverse wavelength, the density fluctuation level drops by about a factor of 3. So it follows the evolution of the shear. And we have now directly compared density fluctuation levels and shear levels, because the Doppler diagnostics gives you both the local shearing rate and the case-specific density fluctuation rate. We find that there's anti-correlation. So the peaks here in the shearing rate are correlated with dips in the fluctuation level, and the anti-correlation coefficient is about 0.5 here at the time when the shear is maximum. And then the other interesting result was that there's not much correlation here between shear and density in the close to the bottom of the well, but very strong anti-correlation here in the high shear region. So this is the red data corresponding to this region here, and then the blue data corresponding to the other side. So this establishes basically that there's anti-correlation between shear and density fluctuations, which points to a zonal flow activity influencing the intermediate scale density fluctuations also. So finally, in summary, we have looked at core electron transport in ITG and intermediate scale core turbulence. Both are found substantially reduced across the LH transitions in low collisionarity H-mode plasmas. The wave number spectrum measured by Doppler backscattering and TGLF gyro simulations indicate that core turbulence reduction is consistent with A cross B shear. Initial gyro multi-scale modeling simulations indicate the dominance of high K turbulence in the core. fixed flux runs are needed now in preparation to allow quantitative comparison to experimentally measured density fluctuation wave number spectra. T over Ti of 1 has been achieved with central ECH added to these plasmas. We find that there's reduced E cross B shear, and we think this is a very interesting regime for studying electron transport, because in this case electrons and ions are completely decoupled collisionally. The DBS data also indicate that intermediate scale turbulence regulation by zonal flow tends to occur in an electron ITB near the Q equals 2 rational surface. Thanks very much. I'm sorry if I ran over a little bit. So.
When there is this transition between ITG to TE and turbulence, do you see in the measurements a change of the phase velocity in the co-moving frame?
With Doppler backscattering in a heavily rotating plasma, you cannot directly see the phase velocity in most instances, simply because the E cross B flow is so strong. Right? So you have, I've tried, for example, for the ETG regimes, and there's some promise to be able to do it for the ETG mode because the phase velocity is much larger. But normally the E cross B velocity is 10 to 20 times larger than the phase velocity that you get from a linear calculation.
I'm aware of, I will use that as well, but since you might have a different measurement of the radial electric field from the
yes, that's what I'm saying. For ETG, it's very promising to do this because we have CR measurements and then we have the Doppler backscattering itself, and that I can already tell you that there are differences, but I have to still check the direction. Whether it's electron or ion diamagnetic, and I haven't done a profile yet also. So. But it's very difficult to do it for ITG.
Other questions? Turning you down. Yes.
Just a comment, perhaps. Isn't it worrying that so much of your confinement improvement actually comes from the beams, since you won't have them in a reactor?
You in terms of the shear, just generating enough shear. Yeah. Well, the interesting thing is that I haven't had time to show this, but when you use these same plasmas and you ramp down the rotation by using co-beams, right? These are all discharges that are started with counter injection, although that in itself is not material. But when you ramp down the rotation towards a balanced situation, the confinement actually improves. And we don't quite know yet whether that's a local improvement that has to do with the pedestal or the region just inside the pedestal, or whether there's other effects going on. But global energy confinement actually improves in some cases in these plasmas if the rotation is ramped down. But you lose the central confinement clearly. I mean, you don't have a central barrier anymore. So what I'm trying to say is, I guess, that the toroidal rotation and the toroidal rotation shear can behave quite differently.
Okay. Please.
Is anything known about the magnetic shear in this last case?
These are slightly reversed shear plasmas, but not in the. When you typically think of electron transport barriers in a reverse shear say of 2 to 3, it's not anywhere close to that. It's 0.3, 0.4, and it tends to become normal shear as the discharge goes on. So in the early phase, up to about after the LH transition, it's still reverse shear, but very mildly, and then it goes into normal eventually. So the Q is all staying around 2 for most of the core plasma, with then the increase at the outside.
Clive.
In that case, we have anti-correlation between the shear and the density fluctuation. Do you see that in any other cases? I mean, you show that is the case in ITV.
Yes.
But you see like modulation when it's out in ITV or near the edge or in any other cases.
But as you can imagine, we have tried to look at the LH transition. So far, we don't see it before the LH transition, except maybe in the very last time slice before the transition. But the problem is that there's a certain amount of statistics required to make this credible, and so I still have to convince myself that this is real. But when you normally look in a plasma that does not have much shear or no localized shear features, we don't see this. We don't see this anti-correlation.
All right, why don't we thank Lothar again.